For those who love exploring and observing the bright stars in the night sky, concepts like comets, meteoroids, and asteroids are familiar. They are fragments of matter wandering through the expanses of space, becoming regular visitors to our solar system and interacting with observable orbits from Earth. Some comets even establish fixed orbits that can be observed periodically. This is where a new issue arises. You may not be aware that all comets and asteroids found today have their origins in the solar system. That's why Oumuamua became special. Oumuamua was first discovered by astronomers in October 2017. It is the first interstellar object to visit our solar system with an unusual orbit. Initial reports about Oumuamua's peculiar characteristics led some to speculate that the object could be an extraterrestrial spacecraft sent from a distant civilization to investigate life within our solar system. However, these claims remain unverified. Therefore, in today's video we will review the evidence and shed light on the mysteries surrounding this enigmatic object. Is it an extraordinary comet or part of a mysterious plot from other realms of space? Oumuamua, as the first interstellar object to visit the solar system from another region of space, immediately captured the attention of the scientific community and the general public through various media outlets. Countless hypotheses were formulated based on the object's peculiar characteristics and unclear origin. This included rumors and ambiguous information about extraterrestrial spacecraft. Unlike most other comets, Oumuamua lacked a bright coma or a dust tail. Its peculiar shape, resembling a cigar or a double pancake, and its small size suggested it resembled an asteroid more than a typical comet. However, the puzzling acceleration of Oumuamua away from the Sun in a manner that astronomers couldn't explain left scientists bewildered. Some speculated that it could be an extraterrestrial spacecraft. At the University of California, Berkeley, an astronomer and a planetary scientist from Cornell University suggested that the mysterious deviation of it from its hyperbolic trajectory around the Sun could be explained by a simple physical mechanism commonly observed in many icy comets: the release of hydrogen gas as the comet heats up under the Sun's radiation. What sets Oumuamua apart from other carefully studied comets in our solar system is its size. It is small to the extent that gravitational forces acting on it are slightly altered by the tiny thrust generated when hydrogen gas escapes from the ice. Most comets are essentially dirty snowballs that periodically approach the Sun from beyond our solar system. When warmed by sunlight, comets release water and other molecules, creating a bright coma or a cone-like region around them, often accompanied by gas and dust tails. The expelled gas acts like a propulsion system on a spacecraft, giving comets a slight kick that changes their trajectory slightly from the typical elliptical orbits of other objects in the solar system, such as asteroids and planets. When discovered, Oumuamua lacked a coma or a tail and was too small and too far from the Sun to release enough energy to produce significant outgassing. This led astronomers to speculate wildly about its composition and what propelled it outward. Was it an iceberg-like block containing hydrogen releasing hydrogen gas, or was its nature that of a large porous snowflake pushed by the gentle pressure of the Sun, a light sail created by an extraterrestrial civilization, or a spacecraft propelled by its own means? Jennifer Bergner, an assistant professor of chemistry at UC Berkeley specializing in studying chemical reactions occurring on icy surfaces in the frigid vacuum of space, proposed a potentially simpler explanation. She discussed this idea with her colleague Darrell Seligman, currently a National Science Foundation graduate research fellow at Cornell University, and they decided to collaborate to test it. Essentially, a comet moving through the space between stars will be subjected to cosmic radiation, causing the ice to cook and form hydrogen. Therefore, their hypothesis was, if this happens, could Oumuamua actually trap it within its body so that when it enters the solar system and gets heated it would release more hydrogen gas? Bergner raised the question, could that produce the force needed to explain the non-gravitational acceleration? Quantitatively surprisingly, she discovered that experimental studies published in the 1970s, 80s, and 90s demonstrated that when ice is bombarded by high-energy particles similar to cosmic rays, a significant amount of hydrogen molecules is created and trapped within the ice. In fact, cosmic rays can penetrate ice for tens of meters, turning a quarter of the water into hydrogen gas. For a comet with a diameter of a few kilometers, the amount of gas escaping would come from a very thin shell compared to the majority of the object. Thus, in terms of structure and considering any acceleration, it is not necessarily an effect that can be detectable. However, because Oumuamua is so small, scientists had to consider that it actually generates enough force to account for this acceleration. Initial studies and images suggested that the mysterious object had a reddish hue with estimated dimensions falling around 115 m x 111 m x 19 m. However, astronomers couldn't be certain about the actual size as it was too small and too far for telescopes to resolve. The size had to be inferred from the brightness of the comet and how it changed as the comet sped away. To date, all comets observed in our solar system, short-period comets originating from the Kuiper belt and long-period comets from the more distant Oort cloud, have diameters ranging from about 1 kilometer to hundreds of kilometers. What's particularly unique about Jenny's idea is that it precisely aligns with what would happen to comets between stars. We have all sorts of wild ideas like hydrogen iceberg blocks and other crazy things, and those are just the broadest, most general explanations. Comets have been mysterious celestial bodies in our solar system for centuries. For a long time they were viewed as ominous omens appearing and disappearing, creating a sense of the eerie and even fear. It wasn't until later, with the development of science, that it became known that comets are merely remnants of ice and rock from the formation of the solar system about 4.5 billion years ago. They serve as records of the conditions present during the early stages of our solar system. Comets between stars can also offer clues about the conditions around other stars surrounded by planet-forming disks. They act like snapshots of what our solar system looked like during its evolution, akin to the current protoplanetary disks. Therefore, studying them is a way to look back at how our solar system appeared during its formative stages. Planetary systems in other galaxies also seem to have comets, and some of them might be ejected due to gravitational interactions with other objects in the system, a phenomenon astronomers believe has occurred in the history of our own solar system. Some of these interstellar comets occasionally enter our solar system, providing opportunities to learn about planet formation in other systems. According to Seligman, these comets and asteroids within our solar system have taught us more about planet formation than what we've learned from actual planets within our solar system. He believes that comets between stars may reveal more about planets outside our solar system than the exoplanets we are currently trying to measure. Most comets that we observe today come from distant regions of the solar system, originating in places known as the Kuiper belt, extending from the orbit of Neptune, and the Oort cloud forming the outermost part of the solar system. The orbits of comets are highly elliptical, with a center at the Sun, and the far end sometimes extending well beyond the orbits of Neptune or Pluto. Occasionally, the orbits of comets will bring them into direct contact with other celestial bodies in our solar system. The gravitational influence of various planets and the Sun shape their orbits, making such collisions more likely. As comets make numerous trips around the Sun as they approach the hottest source in the solar system, the intense radiation begins to vaporize their gases and ices, creating a bright cloud around the object, officially known as the comet's coma. This cloud can extend for thousands of kilometers when we observe comets from Earth. This coma is often what we perceive as the head of the comet. On the other hand, radiation pressure from the Sun pushes material away from the comet, forming two tails. The first tail is the dust tail and the second tail is the gas tail, plasma tail, formed from gases vaporized from the nucleus and energized by interactions with the solar wind. Dust from the tail is left behind like a breadcrumb trail, indicating the path the comet has taken through the solar system. The gas tail is often challenging to see with the naked eye, but a photograph reveals it shining with a bright blue color, extending directly away from the Sun, and influenced by the solar wind it typically stretches over a distance equal to the Sun's distance to Earth. Based on these characteristics, Oumuamua indeed doesn't resemble a typical comet. Prior to this, astronomers had published numerous papers on what could be learned from observing any interstellar comets between stars in our solar system, and then came Oumuamua. On October 19, 2017, on the island of Maui, astronomers using the Pan-STARRS-1 telescope operated by the Institute for Astronomy at the University of Hawaii at Manoa first spotted what they thought was a comet or asteroid. Upon realizing its inclined orbit and high speed of 87 km per second, suggesting it originated from outside our solar system, they named it One-Eye Oumuamua Hawaiian, for a messenger from afar arriving first. It was the first known interstellar object beyond the dust particles ever seen in our solar system. The second such object is 2I Borisov, discovered in 2019, although it looks and behaves more like a typical comet. As more astronomical observations focused on Oumuamua, astronomers were able to map its orbit and determine that it had passed through our solar system on a hyperbolic trajectory closely skimming the Sun's gravitational influence and then heading back into interstellar space, most likely toward the constellation Lyra. They found that the object's closest approach to Earth occurred on September 8, 2017, about 24 million kilometers from our planet. At the time of its closest approach, Oumuamua was the most active object ever seen by the Sun, although its brightness quickly faded as it departed. In conclusion, while the mystery surrounding Oumuamua has drawn substantial interest, its role as the first interstellar object observed in our solar system offers a unique opportunity to deepen our understanding of celestial bodies and their formation processes in the cosmos. Scientists and astronomers are now excited about the prospect of studying future interstellar comets, including any that may follow in Oumuamua's path. As humanity continues to explore the universe, the ongoing study of such objects may unlock further secrets about the origins of our solar system and those beyond, providing valuable insights into the broader context of our existence in the cosmos.